In this example of Bayesian hypothesis testing, we assume that some proportion of components made of particular materials are faulty. By sampling components of material A versus components of material B, we want to be able to determine which material is better, i.e. less likely to be faulty. Here's the Bayesian model that we're going to use for this. So we're going to start by assuming that the probability that either material is faulty is a uniform distribution. So we're going to have total uncertainty about either of these materials. There could be anything between 0 and 1, the underlying probability that these are faulty. So there you can see we've defined the uniform distribution. Of course, we could have defined some other distribution which captures some prior knowledge, and we'll see the impact of that later on. We want to test the hypothesis that material A is better than material B against the alternative that material A is not better than material B. So how is this hypothesis node defined? Let's look at its definition. It simply says that if the probability of material A is faulty is less than the probability that material B is faulty, then the hypothesis is true, else it's false. The way we define the number of faults found is of course just a binomial distribution. So the number of A that are faulty has a binomial distribution where n, the number inspected, and p, the probability that that material A is faulty. And similarly, material B defined in exactly the same way. So now what we'll do is we'll start to enter evidence about number of components of material A inspected and how many were faulty. Suppose we inspected 100 of A, and we discovered that, let's say, 10 of these were faulty. And for B, let's suppose that we only inspected 50, and that 5 of these were faulty. When we run the model, we see that the evidence shifts slightly in favour of material A, even though the proportion of faults was the same 10% for both. And that's because we're more uncertain about the probability of B than the probability of A because of the smaller sample size for B. So let's suppose we have a bigger sample size. Suppose we inspect 200, and that 20 of these are faulty. So again, it's the same 10% proportion, but it's a bigger sample size. What happens now? Look how the probability distribution of B is now less uncertain than A, and that shifts the evidence slightly to favour material B. So now suppose that we have 400A inspected, and that only 30 of these are faulty. So it's a bigger sample, and now a smaller than 10% proportion are faulty. When we run the model now, the probability that material A is better is now over 85%. And if we observe, let's say, 500 of A and still had only 30 which were faulty, then we run the model, the probability that material A is better than B is now over 95%. Finally, let's see how different things will be if we make a different prior assumption about the probability of B being faulty. Let's actually suppose that instead of a uniform distribution, it's a triangle distribution where the minimum value is 0, the maximum value is 0.05, so that's 5%, and the middle value is just 1%. When we run the model with exactly the same observations as we had before, despite those observations, we still conclude that material A is not better than material B with 95% probability because of that incredibly strong prior belief in the high quality of material B.